Hi everyone, I'm Yu-Hsiang. I'm a PhD student at UC San Diego. Now I'm going to present our work ultra-fast and ultra-large multiple sequence alignments using TWILIGHT. Here's the outline. First, I'll briefly introduce multiple sequence alignments, focusing on applications and limitations of current multiple sequence alignment tools. Next, I'll introduce our work TWILIGHT, total and wide alignments at high throughput. And then I'll talk about our key contribution and the results. And next, I will go to conclusion and future work. At the end, I will show how to install and run Twilight on our computers. Multiple sequence alignment, also known as MSA, is just like a pairwise alignment, but instead you try to align more than two sequences. The goal of MSA is to maximize the overall similarity and to preserve evolutionary or structural relationship between multiple sequences. Multiple sequence alignment is a cornerstone of many bioinformatics application. So I'll name a few here. First of all, multiple sequence alignment can help identify sequence homology and functional region of the genome. It can also help infer evolutionary tree. So in this tool RODIS here, as you can see, multiple sequence alignment, which is circled by a red square, plays an important role in this whole pipeline. It can help estimate the gene trees, and the final species tree will be inferred from those gene trees. MSA can also help constructing and analyze pangenomes. So in the past, people usually align new genome assemblies to a reference genome, but in this case, some information such as insertion to a reference genome might be discarded and it may result in information loss. So pangenome is a collection of multiple genomes here. As you can see in the figure, it's usually represented by a graph. So all the information, for example, deletion, insertion, or inversion, or duplication of all the genome can be preserved here. There's a tool called PanMan. It's apply a compression technique to a pangenome to reduce the overall file size without losing information. As you can see in his overview figure, it can also take the MSA as inputs. And the last, MSA can also be served as a training data for bioinformatic related machine learning models. The most well-known one is called AlphaFold here. As you can see in its pipeline, it also accepts MSA as inputs. We have many powerful MSA tools here, but we still face some key limitations. First, current tools are still too slow to keep up with the high throughput genome sequencing. As you can see in the table here, when aligned 100K sequences, although math is the fastest, but math have lower accuracy compared to pasta or megas. If we aim to achieve high accuracy and use pasta or megas, we may take hours for just 100K short sequences. And another limitation is that this tool often struggle with very long or very large scale sequences. As you can see in the table here, if we increase the sequence length from 1500 to 10K, accurate tool like pasta and megas cannot finish the alignment in 24 hours. Now I'll introduce our work Twilight. Here's a Twilight overview. Twilight accepts a row sequence file in pasta format and a guide tree file in new format as inputs and outputs the final alignment in pasta format. At a very high level, you can view Twilight as an accelerator for progressive alignment. We also have the support of divide and conquer strategy in Twilight, but unlike previous work such as Pasta and Megas, the divide and conquer strategy does not help improve accuracy or speed in Twilight. It only helps reduce peak memory consumption. Twilight adopts some newly introduced algorithms like Calco algorithm and removing gappy color heuristic to speed up the process. Another good thing of Twilight is that it is highly parallelized and make it effectively leverage the power of modern HPC platform. Now let's talk about the scoring scheme in Twilight. Twilight basically follow the same strategy as cluster W. We first apply a branch proportional sequence weighting strategy to assign a weight to each sequence. And the equation is shown below. The L is the branch length and the O is the number of descendants leaves at that node. And by applying this strategy, we can prevent the alignment from being dominated by a large number of closely related sequences. And to align two alignments, we'll have to first turn the alignment into profiles. A profile is a collection of frequency of each character at each alignment column. An example is shown below. So assume that all sequences have the same weights. We can simply calculate the profile by counting the occurrence of each character divided by the total number of sequences. And to calculate the pairwise column score, we simply add up all the possible pairwise combination of characters and multiply by their frequency. For the dynamic programming algorithm for the alignment, we simply follow the same algorithm as cluster W by using the affine gap penalty with a position-specific gap penalty. And the position-specific gap penalty gives a lower gap penalty to columns where already have one or more gaps in it to make more gaps aligned to each other. Now let's talk about the divide and conquer strategy in Twilight. So to align a very large data set, the memory usage is usually dominated by the sequence storage. To overcome this issue, we have a divide and conquer strategy in Twilight. We first divide the large data set into multiple smaller data sets, and we align them sequentially. And example is shown below, like after each align each subset, we call it a sub-alignment, and we represent the sub-alignment using a binary string and a profile. Since the binary string and the profile is not related to the sequence count, so we can use this to represent a large number of sequence without using much memory. And the zero in the binary string represent existing column, and one means a newly added gap. The example is also shown below here. After uh, after we align all the sub-alignments, we read in the older sub-alignment file and we update the sub-alignment and write into a new file. We do it sequentially for all the sub-alignments to prevent storing all sequences at the same time, and this can significantly reduce the peak memory usage. After all final alignment of sub-alignments is output, when we use a Unix CAX utility to concatenate all the output alignment file to form the final alignments. Twilight use a Needleman algorithm, which is a global alignment algorithm to do the alignment with a affine gap penalty add onto it. So there's a few ways to do the computation of DP equation. The traditional way is to do for matrix computation, but it is not practical because the time and space complexity scales quadratically. So some people propose a banded alignment, which reduces the time and space complexity to linear. However, this still poses a challenge to alignment of very long sequences, as you may need very large memory to store the trustback pointer. So Professor Turakia proposed a tiling algorithm, which enable the storing of trustback pointer using only constant memory. However, the drawback is that this algorithm has a lower accuracy compared to banded alignment or full matrix computation. So a newly introduced algorithm called Talco algorithm at a very high level is improvement of the tiling algorithm. It also only requires constant space to store trustback pointer, which is a good thing because this allows us to store the trustback pointer in a GPU's shared memory and make it able to do the acceleration on GPU for very long sequences. And it also overcome the drawback of low accuracy of tiling algorithm. It can guarantee an optimal alignment under the banded constraint. So due to the neutrality of progressive alignment, once a gap is introduced there, then it will always be there. As a result, the alignment length will be longer and longer, And as we know previously, the alignment algorithms at least scale linear to the sequence length, and therefore when we proceed to the root of the tree, we might observe a slowdown for the alignment step. To overcome this issue, we remove the gappy column, which is a column that consists of more than a certain threshold of gaps before the alignment, and we can therefore reduce the length that will proceed to the alignment step. And this can avoid a substantial slowdown during the alignment step. There are many previous work working on accelerating the DP equation or accelerating sequence alignment on GPU. We simply follow the same strategy as previous work. First, we introduce a scheduling algorithm to first find out all the independent alignment here. As you can see in the figure here, the order one, the D, E, F, G are all independent alignment pair. And we assign one GPU block to one alignment pair, then we can do all the alignment at the same time. Within each alignment, we also assign each thread to calculate the score of a cell in the same waveforms. In TWILIGHT, we also support a multi-GPU parallelism. Now I'll talk about key contribution and results. TWILIGHT demonstrates strong performance in both speed and accuracy. In panel A, as you can see here, TWILIGHT has a comparable accuracy to Magus and Pasta, which is widely known as a very accurate MSA tool. And in terms of runtime, if you look at panel B, TWILIGHT is the only tool that can finish the alignment of 1 million sequences in 24 hours, and TWILIGHT only needs 32 minutes. And TWILIGHT can also be further accelerated by adding more GPUs to it. TWILIGHT also scales linearly with sequence length. In panel A, TWILIGHT is the only tool that can align 10K sequences which has 1 million bases in 24 hours, and TWILIGHT requires only 3.35 hours. And TWILIGHT can effectively leverage the available parallelism. In panel B here, when the number of CPU cores scales from 8 to 128, TWILIGHT achieve almost 50% of efficiency, while other tools can only achieve at most 25% of accuracy. And some tools don't even scale with multiple threads. With the divide and conquer strategy, TWILIGHT can also be adapted to platforms with limited memory constraints, such as personal laptop. From the figure on the right, without the divide and conquer strategy, TWILIGHT requires 130 memory to finish the alignment of 1 million sequences. But by applying the divide and conquer strategy, we can reduce the peak memory consumption to under 16 or even close to 8, which make it even possible to do this large scale of alignment on personal devices. But here comes with some trade-off. The smaller subtrees may reduce the parallelism and introduce overheads from repeating read and write files. And also the accuracy might also be affected because when we try to merge multiple subtrees, we might not follow the original tree topology, so that might result in some minor loss of accuracy. TWILIGHT is originally designed for alignment of very long nucleotide sequences, but now we also support the alignment of large-scale protein dataset. So we test TWILIGHT on a home fin dataset here. As you can see, TWILIGHT is faster than the fastest tool MAFT here. But in terms of accuracy, we have comparable accuracy with cluster omega, but much higher error rates than megas and MAFT. So this part is still in progress, and we aim to close this gap in the near future. Last but not the least, TWILIGHT facilitates the construction of an ultra-large genome of 8 million SARS-CoV-2 sequences. We compare the number of substitution of our multiple sequence alignment to the Austrian mass, and we find 94% of concordance. And when we look at the indels here, we can specifically extract all the indels that are previously reported of the main lineage here. So this demonstrates that our alignment of these very large scale sequences is of very high quality. So here's come to the conclusion and the future work. So in conclusion, we present Twilight and as a tool to overcome the scalability limitation of existing solution. And some well-known feature of Twilight is that we can align 1 million RNA sequences in 32 minutes and 10K sequences of 1 million bases in just 3.35 hours. And to the best of our knowledge, Twilight is the first to perform non-relevant-based MSA on 8 million SARS-CoV-2 sequences. For the future work, as I described before, we try to incorporate more sensitive methods for highly divergent alignments. And we also plan to expand Twilight to a multiple whole genome alignment, which is capable of handling nonlinear genomic rearrangement such as inversion, duplication, and long indels. So for acknowledgement, I would like to thank my co-authors, Amit Walier, and also Professor Yatish Turakia, and all other people that helped us during our developments. Now I will show how to install and run Twilight. First, we'll have to go to the Twilight's GitHub page. So you can directly visit this link below, or you can search Turakia Lab on Google and click Tools and click the README under the Twilight's icons. This can also lead you to Twilight's GitHub page. So it provides a very detailed installation instruction on our GitHub page. You can simply follow the instruction there to install Twilight. We also provide a variety of installation methods. So I would recommend using Conda to install it, since it does not require a sudo access if you're working on a Linux platform. If you plan to install Twilight from source, we also provide an installation script that can make all the process more easier. So as I mentioned before, Twilight requires input guide tree and a row sequence file. You can specify the guide tree with the -t option and the input sequence file with the -i option, and also specifying the output file name with the -o option. We can also specify the number of CPUs that you would like to use and the GPU number of GPUs that you would like to use by -C and -G. If you want to run with the divide and conquer method, you can use -m to limit the maximum subtree size. Since a guide tree is not always available, so we also provide a dynamic workflow that integrates other tree inference tool with Twilight here. You can simply follow the instruction on GitHub page to download all the dependency of this iterative mode. So for the initial guide tree, we provide 3 options. First, you can use math tree or part tree or MAPT's default tree algorithm. And with subsequent iteration, we use maximum likelihood-based tree inference tools such as best tree, RuxML, and IQ tree. So we also show results here. The combination of Twilight and Fast tree is 4 times faster than Pasta. But in this case, Fast tree took more than 90% of runtime. So if we replace Fast tree with another tool from our lab deeper, we can run 3 iterations in only 46 seconds, which is much faster than Magus or Pasta. And as you can see here, we also achieve a good alignment error rate and tree error rate. So that's all I have for today. Thank you for listening.